Today we're going to be talking about finding trig functions at any angle. Previously, our setup required that our angle be acute, meaning part of a particular right triangle. So previously, if we had something that was in the second quadrant, third, or fourth quadrants, what we ended up doing is creating a right triangle and finding the values separately. So here's an example of an angle in the second quadrant. And the only way to have solved this previously was to form a right triangle using the x and y components and treat this as an acute angle here instead of using the angle from the positive x-axis. So today we're going to talk about how to do this regardless of how large or small the angle is. So we're going to have slightly new definitions of our trig functions, but they're based on the same fundamentals that we learned before. So now when we talk about sine of theta, so again, our angle here is somewhere in the second quadrant. We could also do this in the third or fourth quadrant, but our sine is going to be based on our angle theta, and it's going to be equal to the opposite side over the hypotenuse. But again, we don't have a right triangle from this angle. So we're essentially using a trick where we temporarily create another right triangle here that's going to have the same characteristics with a slightly different angle. So here, if we wanted its sine, it would be equal to our opposite side, which in this case is y. So it's going to be y over our hypotenuse, which is the radial length here, r. Now, r can be found by using the Pythagorean theorem and the coordinates. So x squared and y squared would give me a squared plus b squared, and that would equal c squared, in this case, r squared. And so if we want to solve for r, or the hypotenuse, we take the square root of both sides. So since this is a distance or a length, it's always going to be positive. So our hypotenuse is going to be positive. But in this case, our x value would be negative and our y value would be positive. We're using this triangle, but we're actually finding it from this larger angle theta. So our sine would be y over r. Our cosine is going to be x over r. Our tangent is going to be y over x. Our cosecant is going to be r over y. Our secant is going to be r over x. And our cotangent is going to be x over y. Now, the reason this is done separately is because these actually have a slight restriction where we previously did not have. So if we look at tangent and cosecant and secant and cotangent, all of them have an x or y in the denominator. But we know when we look at the unit circle, so in finding angles on the unit circle, there are some angles where it's impossible to form a right triangle in this way. And those four angles are on the positive x-axis, where the point is 1, 0, the positive y-axis, where the point is 0, 1, the negative x-axis, negative 1, 0, and the negative y-axis, 0, negative 1. Now, at these points, it's impossible to form this right triangle. So the trick that we did previously will no longer work because you can't form acute angles. Essentially, instead of a triangle, we have a line. So finding trig functions at any angle for angles that fall in the first, second, or third quadrant, we could form a alternative right triangle, And that would give us these values here: y over r, x over r, y over x, so forth and so on. But for the points in between the quadrants, known as the quadrantal angles, these points don't follow the same rules, and since they don't form a right triangle, issues occur when x or y are 0, because for our trig functions, 4 of them, tangent, cotangent, cosecant, and secant, have an x or a y in the denominator, and because they have an x or a y in the denominator, these values cannot be 0. So if we look at 1 comma 0, our x value is 1. So that means cosine of theta equals 1. Sine of theta equals 0. Some of these other trig functions aren't going to be defined. Tangent is simply y over x, or 0 divided by 1, which is just going to be 0. But cotangent is 1 divided by 0. So cotangent, on the other hand, of theta is going to be undefined. Again, cosecant is also going to have a problem. So cosecant is the reciprocal of sine. So cosecant of theta is also going to be undefined, as we can't divide by 0. So we have a radial length. Regardless, it doesn't matter how big our r is, we still can't divide by 0. So anytime our x or y are 0 and we're trying to divide by one of those, it's going to be undefined. So secant in this case is defined as r divided by y, or in this case, 1. So even though this is on the unit circle, this would apply for any r. We can't divide by 0, and so for an r of 20, our cosine would, instead of being 1, would be 20. Our sine would still be 0. Our tangent would still be 0. Any of the ones that are undefined, those values would still be undefined regardless of the dilation of how big or small r is. Now for this quadrantal in between the first and second quadrant, our x value is now 0 and our y value is 1, or whatever our r is. So if that's the case, then any of the ones that divide by x, in this case tangent and secant, are going to be undefined. And the others will be defined as previously on the unit circle, our r being 1, our cosine is going to be 0, our sine is going to be 1, and our tangent's going to be undefined, our cotangent is going to be 0, our secant is going to be undefined, and our cosecant is going to be r divided by 1. So if it's on the unit circle, it's going to be 1. In between the second and third quadrant, again, our x value is going to be -1, and our y value is 0. So that means cosecant and cotangent are going to be undefined. And finally, down here, our x value is 0, so tangent and secant are going to be undefined. So anytime we're trying to find an angle that falls in between quadrants, we are not going to have our simple basic definition like we had up here where you can form a right triangle. For the rest of them, we can similarly form a right triangle. And if that's the case, you're basically applying the same techniques you did on the unit circle. You're forming a right triangle, you're finding that r value, because that r value is the hypotenuse. Essentially, a bigger r value means that we have a bigger magnification or dilation. So if we have an r value of 20, it means that we have something that's the unit circle, but we've multiplied that hypotenuse value by 20, which means our x value is going to be 20 times as big and the y value is going to be 20 times as big. We're just scaling the whole thing up. And so that's where we can use these y over r, x over r, or opposite over hypotenuse, adjacent over hypotenuse, in order to define them as these acute triangles. We're going to use what's called a reference angle. If it's in the second quadrant, our reference angle for this angle here would be this theta here. So that's going to be a value between where our line is and 180 degrees. If it's in the third quadrant, our reference angle is right here. And in the fourth quadrant, our reference angle is right here. So reference angles are the acute angle between the terminal side, or wherever the line is, and the x-axis, either positive or negative. And we specifically use these reference angles because this keeps the notation where sine equals y and cosine equals x. Whereas if we define them separately or differently, which we could do, we could say, oh, instead of with the x-axis here, we could find the angle with the y-axis. And if we did that, our opposite and our adjacents would be reversed, so these rules would no longer apply. So whenever we're finding an angle that's not acute, that's larger than 90, we're going to use the reference angle, as in here, to form our right triangle so that sine is always equal to the y over r and cosine is always equal to the x over r. So this is why it is a reference angle, because we're predefining it as this is the convention or the way we're going to do it always. So let's say that we're given a terminal point is 7 comma -4, and they're not giving us an angle. So if we're to find this, this point would be somewhere in the fourth quadrant, okay, over 7 and down 4. But essentially we'd form a line looking like this, and our r would be the length between the origin and this point. So if we're doing this, we could form a right triangle using the x and y coordinates. In this case, the x value would be 7 and the y value would be -4. But that only works if you use this angle theta. If we were to use this other angle, then our triangle would look like this. It would still be down 4 over 7, but our opposite side would be our x and our adjacent side would be y, so these definitions would not apply. But if we use the reference angle, then the definitions apply perfectly, where our y is always going to be opposite if our angle's always adjacent to the x-axis. So if you're trying to solve a problem like this where you're given this point, the first thing we want to do is we want to find out our r value. Okay, so to find r, we're going to use the Pythagorean theorem, or the distance formula between 0 and this point, and that's going to be the square root of 7 squared plus -4 squared. That's going to equal our r. So 7 squared is 49, and -4 squared is 16. So we get the square root of 49 plus 16, which is going to be the square root of 65. So if we're trying to find the trig functions for this, our sine is going to be y over r, which in this case, our y value is -4, and our r is root 65, which we're going to rationalize by multiplying by root 65 over root 65, and we're going to get a simplified -4 root 65 over 65. So that's our sine. Our cosine is going to be the x divided by r, which will be 7 divided by root 65, which when we rationalize is going to be 7 root 65 over 65. And for tangent, it's going to be y over x, which is going to be -4 over 7. Now to find cosecant, secant, and cotangent, we simply reciprocate each of these. So cotangent will be -7 over 4, secant will be root 65 over 7, and cosecant will be -root 65 over 4. Now, in order to find reference angles, since they're always going to be adjacent to the positive x-axis, it depends on what quadrant you're in as to how you find it. So if you're in the first quadrant, our reference angle will equal theta. Reference angle, and we'll say quadrant. So quadrant. So in the first quadrant, our reference angle and theta are the same. So both of them are going to be theta. In the second quadrant, our reference angle, instead of being theta, is going to be 180 degrees minus theta. Because essentially we want what is left of that angle going to 180. So if we want this value here, we're going to take 180, which is going all the way over here, and subtract whatever our theta was. In the third quadrant, okay, now we want values that are above 180. So now we're going to have, instead of taking 180 and subtracting theta, we're going to take theta and subtract 180 degrees. And the reason we're doing that is because our theta is going to be bigger than 180. And if we subtract 180, it's just going to give us what's left over in the third quadrant from this x-axis down. For the fourth quadrant, we want an acute angle over here. And this angle is how much is left between our theta and our full circle, or 360 degrees. So we're going to have 360 degrees minus theta. So this is how you find a particular reference angle that's on the unit circle in the first, second, third, or fourth quadrants. If our angle is in radians, it will be done similarly, where in the first quadrant, it's just going to be theta. In the second quadrant, it's going to be pi minus theta. In the third quadrant, it's going to be theta minus pi. And in the fourth quadrant, it's going to be 2 pi minus theta. Now, another thing to keep in mind is our angles can be negative and they can be bigger than 360 degrees. So if this is the case, what you end up doing is you end up either adding or subtracting 360 degrees or 2 pi until our angle falls in the original unit circle between 0 and 360. So for example, if our angle was, so it's 540 degrees, we'd originally subtract 360, and now our angle would be 180 degrees. So now it does fall in the unit circle, and this is a quadrantal. If we had a value that was like 570, again, we'd subtract the 360, and now we'd have 210. But this doesn't give the reference angle. This gives a new theta that's going to be equivalent. And so now we need to recognize which quadrant this is in. So this would be in the third quadrant. And so since it's in the third quadrant, we're going to take this and we're going to subtract 180 degrees. So 210 minus 180 degrees, and that's going to give us a reference angle of 30 degrees. Now, let's go through a couple other examples. So let's say that we had an angle of 7 pi over 9. So theta equals 7 pi over 9. If we wanted to convert this to its reference angle, we need to identify which quadrant it is in. So 7 pi over 9 is going to be in the second quadrant because it's less than pi, but it's more than pi over 2. So since it's in the second quadrant, we're going to take pi and we're going to subtract 7 pi over 9. And when we do that, we're going to get 2 pi over 9. So the reference angle here would be 2 pi over 9. So let's say that we have an angle 290 degrees. So again, identify which quadrant it's in. So this is more than 180, so it's in the third or fourth quadrant, and it's more than 270, so it's in the fourth quadrant. So we're going to take 360 degrees and subtract this 290, and we're going to get 70 degrees is our reference angle. These reference angles can be used to find trig values of any particular angle. Let's say that we're given the sine of 5 pi over 3. So if we're given the sine of 5 pi over 3, this is going to be in the fourth quadrant. So what we would do is we'd say 2 pi minus 5 pi over 3 equals pi over 3, because this is equivalent to 6 pi over 3 minus 5 pi over 3, which is pi over 3. And once we have that reference angle, we essentially have a triangle that's in the fourth quadrant that's going to be going over and down. That's going to have an angle of pi over 3. Now, pi over 3 is one of the common or basic angles that we know from before. So this is essentially a 60-degree angle. The adjacent side here, the x, is going to be 1/2, and it's going to be positive because we're in the fourth quadrant, but our y is going to be negative root 3 over 2, and our hypotenuse is 1. So if we wanted to evaluate the sine of 5 pi over 3, we want the y value, which is just simply going to be negative root 3 over 2. And again, we know it's negative because the quadrant that it's in. If we wanted the cosine of negative 60 degrees. So with the negative angle, instead of going counterclockwise around the unit circle, so again, if our unit circle is like this, we normally go in this direction. Negative signs mean to go the other way. So that would mean it would be a 60-degree angle right here in the negative direction, or clockwise. So negative 60 degrees is equivalent to 5 pi over 3. So what we do, again, negative 60 degrees, we want to put it on the unit circle. So we'd add 360, and then it would become 300 degrees. And then to find the reference angle, we would take, since this is in the fourth quadrant, we take 360 degrees, subtract 300 degrees, and we'd get 60 degrees. So essentially, it is equivalent to the cosine of 60 degrees. However, because it's in the fourth quadrant, any y values are going to be negative. So since cosine's really only asking about x, it's equal to the cosine of 60 degrees. So the cosine of 60 degrees is simply 1/2. If they ask the sine of negative 60, so the sine of negative 60, because this is in the fourth quadrant, it would instead be negative √3/2. Because the sine of 60 degrees is √3/2, positive. But because it's in the fourth quadrant, y values are negative. Another example, let's say that we have the tangent of 17 pi over 6. So 17 pi over 6. So this is not in the first 2 pi or 360 degrees. So we're going to take this 17 pi over 6 and we're going to subtract 2 pi or a full circle until we get it in the unit circle. So 2 pi would be 12 pi over 6. So 17 pi minus 12 pi over 6 is going to be 5 pi over 6. 5 pi over 6 is in the second quadrant. So if we were to draw our triangle, we would have a triangle that looks like this, where this is a 5 pi over 6. This would be a 30-degree angle. So again, to convert to the reference angle, we would take pi minus 5 pi over 6, and we would get pi over 6, or 30 degrees. So now that we have that this is in the second quadrant and essentially equivalent to a 30-degree angle, we can now write our values. So again, the opposite side would be 1/2, and this is going to be negative √3/2. So when we're doing tangent, we're doing opposite over adjacent. So tangent of 17 pi over 6 is going to equal 1/2 divided by negative √3/2. So times 2 over √3, negative 2 over √3. Our 2's are going to cancel, and we're going to be left with negative 1 over √3, and when we rationalize it, negative √3/3. The main idea I want you to understand is that when you're trying to find any random trig function given an angle, that you can always translate it into a simpler angle that's going to fall as an either acute angle or as a quadrantal angle. But once you simplify it, you have to make sure you check your signs. So again, if your value's in the first quadrant, then your x and y are both positive. So that means sine, cosine, tangent, cosecant, secant, and cotangent are all going to be positive. If you're in the second quadrant, your y is positive, but your x is negative. So I'm going to make a little table here to show you what happens to each trig function. So we're going to say sine, cosine, tangent, cosecant, secant, cotangent, and we're going to say quadrant. Use a Q. So in the first quadrant, because x and y are both positive, all of these are going to be positive. In the second quadrant, our y is positive, but our x is negative. And so sine, which is based on y, stays positive, but cosine becomes negative. Tangent, which is y over x, if one of them is negative, but the other one's positive, that's going to make tangent negative. And if tangent's negative, cotangent is also going to be negative for the same reasons. Now, cosecant is the reciprocal of sine, so if sine's positive, cosecant's positive. But secant, being the reciprocal of cosine, if cosine's negative, secant will also be negative. In the third quadrant, okay, both y and x are negative, so sine's negative, cosine's negative. Tangent, though, because it's a ratio of y over x, is actually going to be positive because a negative divided by a negative is a positive. And for the same reason, cotangent is going to be positive. But cosecant and secant are both going to be negative because both sine and cosine are negative. In the fourth quadrant, our x is going to be positive and our y is going to be negative. So sine is going to be negative, cosine is going to be positive, tangent is going to be negative because, again, one of these two is negative, but the other one's positive. So when we do y over x, we're getting a negative divided by a positive, which is negative. Cosecant is going to be negative because it's the reciprocal of sine. And secant is going to be positive since it's the reciprocal of cosine. And cotangent is going to be negative because it's the reciprocal of tangent, and tangent's negative. So if you notice for each of these trig functions, in two quadrants it is going to be positive and in two quadrants negative. That is the same for each of these trig functions. Half the time they're positive, half the time they're negative, depending upon which quadrant. So the idea here that I want you to understand is that we can simplify any angle, regardless of how big or small it is, regardless of whether it's negative or positive, and equate it to a reference angle. But when you do that and you form this reference angle, or quadrantal angle if it lies on the axis, so when you're doing that translation, you have to keep in mind the signs. And so this table, or simply remembering whether x and y are positive, is going to help you make these smaller, simpler triangles in the second, third, and fourth quadrants, but keep the signs correct. So any right triangle in the second quadrant is going to have a negative for the x and a positive for the y. Any right triangle in the third quadrant is going to have a negative for the x and y. And any one in the fourth quadrant is going to have positive for the x and negative for the y. So each of these right triangles that you form using the reference angle, your trig functions are going to be the same as this triangle, but the signs might be different. So your equivalent triangle in the first quadrant with the same theta here as our reference angle is going to give me the same values for sine, cosine, tangent, cosecant, secant, and cotangent as it would in the first quadrant, with the exception of the signs. So again, in the second quadrant, our sines are still going to be positive and cosecant's going to be positive, but cosine, tangent, secant, and cotangent are all going to be negative. The same thing's true in the third quadrant, where all of them are going to be negative except for tangent and cotangent. And in the fourth quadrant, all of them are going to be negative except for cosine and secant. So that's also another interesting pattern if you're looking at these in rows, is that except for this first quadrant where everything's positive, the other quadrants, only two of the values are positive. So in the second quadrant, it's only going to be sine and cosecant. For the third quadrant, it's only going to be tangent and cotangent that are positive. And in the fourth quadrant, it's only going to be cosine and secant, and the rest of the values are going to be negative.